Yeah, thank you so much. I'll speed up. So I'm Dr. Mohammed Akbar Hussain. I'm the director of Southern Cross Outreach Visibility Project in Australia. So joining me today is my 8-year-old sidekick Zunaira Akbar, who is very keen um, to read the concluding statement if time allows. So Marikh is an Urdu word for planet Mars, and I have chosen this title for our proposed model of human civilization on the red planet. So in this presentation, I have put greater emphasis on things which will be done differently than on Earth, in a unique Martian context using current expertise and technology. So the first, the main challenges humans will face once they get on Mars are the low atmospheric pressure, which is just 0.6% of Earth's atmosphere, essentially vacuum. Low temperatures ranging from minus 50 degrees Celsius on poles at night to plus 20 degrees at equator at midday, with an average of minus 65 degrees Celsius. Then there will be problem of radiation, mainly due to lack of magnetic field on Mars and thin atmosphere, and radiation in form of UV radiation, solar and cosmic radiation will be up to 2.5 times that of experienced on International Space Station. So the other relatively minor issues, but with longer term implications would be lack of breathable oxygen, a lack of surface water, low gravity, just around 1/3 of Earth's gravity, and isolation. So in order to be called an independent parallel civilization on a different world, a million strong Marikh civilization needs to have achieved ability to manufacture all their construction material, equipment, and parts on Mars from the raw material available on Mars itself. They should be able to grow all their food with no reliance on supplies from Earth. They should be able to address all their healthcare needs, and they should have a stable and sustained economy, and they should be able to govern themselves independent of Earth's influence. So, so the basic concept of Marikh settlement is creation of large inflatable structures over craters anywhere from 150 to 500 meters in diameter, which will be interconnected through overground and underground tunnel system. And these inflatable structures can be called crater habitats or crater habs. So the main purpose of such a design is provision of sufficiently large pressurized internal environment where humans can roam freely and spend most of their time without the need for spacesuits in a shirt sleeve environment. Another purpose of such a design is to make use of the depth of crater itself as extra volume of space without the need for additional structural material, and not having to do excavation, as nature has already done that for us during the formation of craters. Now, this modular layout will enable multi-purpose use of each crater hab dedicated to their specific function. These will also provide structural strength and will last a long time against the elements, and they should be able to offer some basic protection from radiation, which we'll talk about in a while. So let's briefly touch the basics of structure and design of a crater hab. So the basic unit, crater hab, will be a hexagonal or isogrid lattice of fabric that must withstand an outward inflation pressure of at least 1 bar. Even though the internal pressure will be maintained at around 0.65 bar, which is equal to roughly El Alto district of La Paz in Bolivia at an altitude of 4,000 meters. The fine structure of the dome will consist of a skeleton of very strong, lightweight fabrics such as Dyneema and segments of silicon fiberglass composite. Both fabrics can withstand tens of kilograms of pressure per square centimeter against the need to withstand at least 1 kilogram per square centimeters to maintain 1 bar of pressure inside the crater hab. So each silicon fiberglass segment will be composed of a woven fiberglass fabric sandwiched between 2 layers of silicon on either side. The whole structure will be an alternate bilayer and trilayer of Dyneema fabric and silicon fiberglass composite bilayer. So if you look at the cross section of a crater habitat, you'll notice that the periphery of the dome here is secured to a system of underground anchors through a concrete sandwich wall, and the roof of the crater hab is connected or secured to the underground concrete anchors through system of Dyneema cables. This is to ensure that the whole structure is held together against an inflation pressure of, say, for a 300 meters crater hab would be equal to roughly 1 million tons of inflation outward pressure. So this is structure designed to withstand such a pressure. So one important aspect of a crater habitat is protection against radiation, both from UV radiations and solar and cosmic rays. So silicon can reflect up to 95% of UV radiation. The crater hab will provide protection against solar wind and cosmic rays using a network of power cables inside the fabric of the dome, while carrying electricity from a nuclear reactor to the interior of the crater habs. In this way, we can generate a weak electromagnetic field, which may be roughly equal to the non-ionizing electromagnetic field under transmission lines, generating up to 10 to 15 microtesla as compared to Earth's magnetic field, which is 25 to 65 microtesla. And for each crater hab, the power required may be around 500 kilowatts to stimulate Earth's magnetic field to reduce cosmic rays to safer levels. So the main idea is why dodge when you can stop. So each individual marine settlement will be a modular system where each area is defined for a specific purpose. There will be crater habs for residential purpose with pod-like houses and open green spaces where residents can roam around freely without the need for spacesuits. There will be different types of residential habs. Some of them would have earth-like houses. Then there will be administration and business crater habs with schools, cafes, and administrative buildings, hospitals, etc. There will be manufacturing and warehouses, crater habs for manufacturing facilities for concrete, plastic, and fabric, and also should have 3D printing facilities. Agriculture and farming can be done in relatively larger crater habs, which will be translucent and maintaining a lower pressure, and will be done through pivot and central command units. There will be transport habitats serving as interchange for Hyperloop interchange, and there will be crater habs for sporting facilities, which will be very important in Martian low gravity environments. So now let's briefly touch the timeline of the development of or establishment of a marine civilization. So considering Mars Direct as one of the most viable ideas for human landing on Mars in existing technology, we could envision first human landing on Mars by year 2030. And by 2040, we can expect 4 Mars Direct bases and a permanent human presence of roughly 100 humans on Mars. And that may be the same year when the first fleet of 20 starships with 200 astronauts and supplies for construction of the first 3 crater hab may land on the surface of Mars. And so this is a brief summary of the logistics of first fleet 2040 with construction equipment, power generation units, and life support equipment, and also water production and waste management facilities. So in summary, the total payload of the first fleet 2040 of 20 starships may be around 1,600 tons with a surplus capacity of 1,400 tons, which will be used as a crew habitat during transit and during stay on Mars after landing during the construction of the first 3 crater habs. So considering the launch cost of $500 per kilogram, the total cost of the first fleet 2040, including the cost of rockets and all the equipment, may sit around $15 to $20 billion, excluding ground support staff, training, and infrastructure. So after the establishment of the first settlement, we can expect an exponential growth of settlements with each 26 months orbital cycle. And by 2060, we can expect that there would be dozens of small individual marine civilization settlements in different locations, all connected through Hyperloop systems. And by 2080, if the population, we can expect the population to have reached around 100, so to reach about 1 million. And by that time, if they have achieved a basic level of self-sufficiency and independence, that may mark the birth of an independent marine civilization. Now, coming to the topic of economy, so no civilization can sustain without a viable model of economy. So this is a brief timeline of the evolution of economy on Mars. So from the time of arrival of the first fleet 2040, to the establishment of the independent Marine civilization. And you can see there's a gradual decline in reliance on supplies from Earth and an increased domestic production and export, and the supplies from Earth will gradually be replaced by imports. So the economy mainly revolves around domestic usage of the items produced on Mars, and a surplus can be exported. The surplus would include an exclusive mineral products from Mars like deuterium-3, or it could be certain medications and chemicals that require low gravity in their production. Earth-based tourism would also be an important source of income for Martian economy, and Earth-based companies can be given advertisement incentives for their role in supporting of establishment of a Martian civilization. Now, in order to create a sustainable source of income for a budding human civilization on a different world, at the very start of establishment of human settlement on Mars, nations on Earth with stakes in colonizing Mars can agree upon signing a treaty to lease out mining rights of helium-3 on Moon to the prospective Martian civilization, should fusion energy becomes a reality as a reliable power source here on Earth. Such a treaty may be signed for up to 100 to 200 years as the best gift of Earth to Mars. Technically, it may be easier to do mining on Earth's moon using Mars as a base because of the, not only for the Martian engineers' expertise of mining in low gravity environment and low pressure environment, but also because of the low gravity of both worlds. It will be easy to for the logistic purposes. And the finished product packed in small volumes can then be shipped directly to Earth. So Mars will always be a power-hungry civilization because of the lack of natural power resources. So in the early period of establishment of marine civilization, solar power will be the mainstay to fulfill the energy requirement because of its ease of setup, safety, and low initial cost. But in the long run, it may not be sufficient to power the requirements of 1 million population, maybe because of the lower output, unreliability in Martian dust storms, and requirement of a huge area. Let's say, for example, my calculations are that for 1 million population requirement, the area for a solar array would exceed 1,000 square kilometers. That will come with a huge maintenance and replacement cost. And that takes us to the nuclear option, initially as an auxiliary and later as primary source of power. So two types of nuclear reactors can be considered in a Martian context. One is the radioisotope thermoelectric generators, which are small and compact but have lower output. These reactors may be used as a backup supply during dust storms to provide bare minimum power to sustain the internal environments only. And then we can, the other option would be much more powerful boiling water reactors, such as small modular reactors, which can utilize permafrost to generate steam directly through fracking by pumping heated air or carbon dioxide underground into the permafrost to utilize the steam thus generated to drive turbines for electricity. The resultant steam can also be released into the atmosphere to start a very early process of terraforming, and the wash regolith in that process can also be used for farming because of the percolate would be washed out in that process. These reactors are compact, have a high output, are long life and reliable, but have a very high cost. Also, transporting these reactors from Earth may carry huge risks unless a local radioactive fuel source could be found on Mars itself. Fuel production. One of the types of fuel that can be produced in great quantities for local consumption is liquid hydrogen and oxygen directly through the electrolysis of permafrost, and the resultant oxygen can also be made available for maintaining the internal environment. But it comes with a high power cost because there is a lot of power required to do the electrolysis of water. Also, it is difficult to store the cryogenic liquids like hydrogen for a prolonged period of time. But because this fuel will be in constant circulation for usage, so that might not be a huge problem. So this is a breakdown of power consumption, which may look similar to that of Iceland, where a major part of energy produced is used in ore processing in Iceland. So that's similar in the Martian context. In all, 1 million strong civilization on Mars may require up to 44,000 megawatts of power at any given time, equivalent to over 1,200 square kilometers of solar array or nearly 150 small modular reactors, or a combination of both. So transport. So the main form of transport on Mars will be Hyperloop system. It will be very efficient in the Martian context because of low gravity and also low atmospheric pressure. So the individual settlements will be connected through Hyperloop system. Suborbital flights may provide quicker means of transport over huge distances, but may be limited to medical retrievals from remote mining settlements and exploration bases due to risks associated with emergency landings in inaccessible areas. Then overland rovers will provide efficient and flexible means of short distance travels. Agriculture and farming. A marine civilization must be self-sufficient in producing entire amount of food needed for sustenance of the society. To make farming successful in a Martian context, the plants chosen to be grown on Mars may be genetically modified in Mars simulation bases on Earth to withstand lower pressures like 0.5 bar or lower, or already be known for their property of growing in low pressure environments. So the type of farming would be traditional earth-based plants. Also, some certain fungi and bacteria may be also used to produce high calorific food. So the food that is produced should have a high calorific value up to at least 55,000 kilocalories per hectare per day. So the larger crater heads, as I mentioned earlier, may be utilized for this purpose, and to sustain a million population, at least 360 square kilometers of farming area may be required, and that could mean 1,800 farming crater heads of 500 meters diameter. There will be an extremely important need for surplus food production in case of any global catastrophe, farming failure, or disease in the plants. So surplus food should be packed in vacuum boxes, and it should be stored, that should be used for many months or years in case of any crisis. These crater hubs will be operated through automation, and it can also be remotely controlled from Earth, so that humans on Mars are spared for other tasks. So talking of the healthcare now, a human society on Mars should be able to address most of their common illnesses, but in a specific Martian context, mental health would be a major issue, including homesickness, loneliness, claustrophobia, anxiety, and depression. Also, constant exposure to low gravity, roughly a third of that of Earth, may take a toll on the strength of muscles and weakening of bones, and can also cause circulation disorders. So creating gravity houses with electromagnets incorporated in its floor, where residents can spend a few hours each day wearing suits impregnated with smart electromagnets, creating an attracting magnetic field by making Earth's gravity, can be a solution to strengthen the bones and muscles. And residents on Mars will need to deal with radiation, especially exposure outside the protected crater haven underground environments, like during mining operations and exploration, transport, and outdoor maintenance works. So brief discussion about the Martian society. So remember, human civilization on Earth started from Stone Age, but human civilization on Mars will start from Space Age. That will strongly reflect in the structure of Martian society. So the gender roles will be influenced by use of technology, and the differences may be limited to the roles in procreation and raising of young ones. The occupations will be mainly mining, exploration, manufacturing, and construction, with a minority working in in-house duties, including running of hospitals, educational institutions, cafes and trades, maintenance of internal environment, IT, and a smaller minority will be employed in law enforcement, research, and administration. You will notice that there will be a lack of defense forces in the early decades of Martian civilization, which will have a very a positive impact on Martian economy and social mindset. So the governance will be a democratic model with experimentation of new governance models and models unique to the Martian way of life. Language, it will be very important to have a unified language on Mars.
Question and answer.
Okay. So let's move quickly then. Education, high importance of education will be, there's just 5 minutes left now?
You have 5 minutes to speak, to finish your presentation.
Okay. All right, thank you so much. The proven record of English as the most unifying language on Earth, and that could be a model for Mars as well, but we can expect a different Martian dialect and accent. So the education, there will be high importance on workplace-based education, local community, schools will be local and community-based, university will be online virtual platforms, and there will be interplanetary educational tours and exchange of students may be a commonplace religion. Many people on Mars may choose to continue their Earth-based faith, but in a Martian context, it may be useful. The religion may be useful for maintenance of mental health and prevention of suicides. And safety algorithms on Mars may become mandatory code of life, which in the long run might start looking like a religion. Literature and art would be reflective of historical references of Earth-based origins and stories of early settlers and their struggles, with the inclusion of new and unique Martian lifestyle and experiences. The demography, million population will be scattered in 50 or so individual settlements, with a mix of children up to 20%, elderly maybe 10 to 20%, which will be mostly early settlers, and adults make up to 60%. Gender distribution will be roughly 50 and 50. And permanent settlers may be 75 to 85%, with the temporary settlers maybe around 15 to 20 or 25%. All right, so this is very important. So the best geographic location for establishing these settlements will be between 40s and 50s latitude in both hemispheres. Any closer to equator may mean lack of permafrost and subsurface glaciers, and any closer to poles may mean lack of sunlight for farming and power generation. However, a few settlements will be located near the poles due to their access to water ice, and few of the settlements will be closer to other areas because of their proximity to mining resources and mineral resources, and they will be all connected through a Hyperloop system. All right, so on to Zunaira to read the concluding statement of my presentation. Zunaira.
A human settlement on Mars holds many promises for the success of humans as a spacefaring species. Mars was once a dynamic, wet world with every potential of harboring life. It is seemingly dead now, but some of us may find it a moral duty of humanity to sow the seeds of life on it, initially in the form of creating a human civilization there, and in the long run, terraforming the entire planet to make it a living world once again, where rivers flow and life gets to write new chapters in evolution.
Thank you. All right, well, thank you. On to questions now.
Okay, George Rodos, please.
Thank you. It was a beautiful presentation. And
thank you so much.
Very much. A question for you. Why produce liquid hydrogen instead of liquid methane? Conventional aerospace wisdom is that there are several challenges with liquid hydrogen: bigger tanks, bigger spacecraft, you need more power to keep it liquid. So I was curious what drove that design decision.
So first of all, I'm more familiar with liquid hydrogen and oxygen, and secondly, I think that because there is a plenty of availability of permafrost, which will be already liquefying for the power generation, so we can then use that steam and water for electrolysis to produce liquid hydrogen and oxygen. But yeah, I do understand that methane is a more efficient fuel, and I've mentioned the challenges involved in trying to store the cryogenic liquids. But because of my own understanding of electrolysis of water is much better than the methane, so I included that in my model of the Martian civilization power requirement. Fuel production.
Thank you.
Okay, Gary, please.
Yes, very good presentation, Dr. Hussain, and
Thank you.
for your daughter as well. She spoke very clearly and from her heart.
Yeah. Thank you.
Dr. Hussain, one of the things that you didn't mention, or at least I didn't catch, was one of the review criteria says that, ask the question, how can the city-state be made an attractive and enjoyable place to live? Could you address that in a sentence or two?
Yes, so the large volumes.
Five minutes left for more questions.
Okay. So the large volumes of crater habs can be utilized to make it more like Earth-like. And as I mentioned, in the residential crater habs, there may be more Earth-like houses with open green spaces and water bodies. So that would be the first step in making it not only aesthetically pleasant, but also to mitigate any effects of claustrophobia for the humans living there.
Frank, please.
Frank?
Frank?
In terms of the aesthetics, again, can you describe, you did describe that there would be sections established for sports, stadiums, etc. But can you describe that more at on a individual or family level? What kinds of amenities would the inhabitants see on a daily basis?
So as it is a modular structure, individual crater hubs will be there for residential purpose and also for park spaces and shopping centers. So it will be as I initially mentioned in the presentation, that most of the emphasis I have put in is how things will be done mainly in a specific Martian context. So to establish the aesthetics of the crater hub, I think we can just do it in the same, very similar manner as we do it on Earth, which will be because it will be a multicultural and multi-ethnic society. So that will all be dependent upon the specific preferences of people who have made Mars their home. But there will be inclusion of everything that we love and enjoy here on Earth, and the advantage of the huge volume, it will be easy to put in all these places that we have on Earth, like shopping centers, parks, and Earth-like houses.
Analysis, please.
I have a similar question to the previous one, but I would like to say it, and maybe I have a further answer to it. What Team 6 will do to comfort aesthetically the 5 senses of Martians?
Yeah, so one of the things that you might have seen is missing is the outdoor view of the Martian. Now, there is not much to see on Mars except for red dirt. But the borders of the crater hubs can have windows because they won't be having any incident sunlight, so that they'll be naturally protected by sunlight. On the inside, we can make parks, grow trees, create water bodies for fishing, swimming. It's all the detail is in the volume of the crater hub, and that's the whole idea of my design, that we are giving volume of several hundred meters in diameter. So that can be, and because of the modular structure, we can put everything that is aesthetic in a Martian context inside. So senses, yes, vision, and like all 5 senses we'll try to incorporate into by taking advantage of the volume of the crater hubs.
Manuel, please.
Yes, thank you. I would like to ask you to expand, if you could, on the socio-economical aspect that you were describing. You indicated, you skimmed quickly through this, but you mentioned at some point reference to gender roles, indicating that they would be influenced by the use of technology and progression and some other. Could you please elaborate on that point?
Yeah, so as I mentioned, that the human civilization on Earth started from Stone Age. So the gender role has been defined historically from that point. But because of the Martian civilization will start from Space Age, and because we will be using technology, so the gender differences in the role in society would be heavily influenced by technology. That, like in an Earth context, in a traditional role, women seem to be more inclined towards Earth-based duty, house-based duties in most of the cultures. But that might be entirely different on Mars, because most of the housework will be done by robots and the use of technology. So men and women will equally be participating in the mining and exploration and construction. But yes, the difference between men and women may only be limited to the need for reproduction and looking after young ones, which itself will be heavily facilitated by technology. So the main difference is the timeline of starting of Earth human civilization from Stone Age to the start of Martian civilization from Space Age, and that will heavily reflect in the way the structure of the Martian civilization works.
Time's up.
Thank you.